We have a very important, consequential topic today. It's going to inform the way you think about microsystems, microcontrollers for the rest of your days in school and maybe the rest of your life. So that's building it up a lot. But we're introducing the idea of counters and how we make counting banks of memory. So if you think back to your 179, for example, we had the 8-bit and 16-bit timers on that Mega hardware system, the Arduino Mega hardware platform. What we're going to build out today is how do we actually make a piece of circuitry, a piece of hardware that counts and retains a number with a certain, incrementing sequence, or we can even count up, count down, count to a certain range, right? We remember our counters counted up to all ones and then rolled back over to all zeros. We'll look at that functionality. What if we only want to count up partially and then roll back to zero? We'll look at creating the count range of these circuits as well. And it's important to remember that what we're doing here is all on physical circuitry. There's no software activity going on in the way that we're describing these systems. So that's where we're headed today, mainly the idea of counters. Then we're going to add on a few application notes about 7-segment displays and multiplexers. A side note, I guess, related to last lab, obviously it did not work. We were having some software issues on this end with our drivers. We were having some iStudio issues because it doesn't allow you to manually create sequential logic, which is fine. Between then and now, I did find the software packages we need to add in, and we've got notes about how to do that on Brightspace. So next time we'll load up iStudio with modules to run D flip-flops and our JK flip-flops that will allow us to build out all the logic we've been talking about here. So the upcoming lab on Wednesday, we will be building out the things we do today. Just had a minor hiccup with software last time, but it's all functionally in there. So we'll start building out counters in our next lab. So here we go. If you're following along in the book, which you have the complete book online, this is chapter 12, content we're diving into. The big picture idea is we're talking about counters. You definitely recall from last time we went through a sequence of building blocks. I started by just drawing 2 inverters on the board and looping it back on itself to retain a bit. We built out that structure in a few different stages through the SR flip-flop set and reset flip-flop, which would just retain a Q bit. We added some enable gate functionality and then copied the circuit twice, separated by an inverter to build out this JK flip-flop that was edge triggered. And that key point gives us as close as possible to the moment in time which an action is going to occur. So rather than having an unknown activity that's going on while ever the enable bit is high, we now have a specific edge so we can work with exact timing, which is helpful in our system design. So our main kind of working unit here will be the JK flip-flop for building out counters and a lot of future devices. We're going to have some sections on registers, which is where you can queue up bits to be sent over a serial port or to convert them from serial to parallel forms of transmission. Set up the registers that are maybe holding information before they're fed into your CPU if you're talking about a PC. So kind of the holding and manipulation of banks and ones and zeros is all built on the backs of the JK flip-flop. And so we did build out all our logic gates. We talked about adders and some of the lowest level functionality. We really start building up and up and up from this point forward into much larger functional devices. So the JK flip-flop's at the core of that. Remember again that this is a clock edge driven device. The triangular icon here indicates an edge. If it's a rising edge, it looks like just a notch here. If it's a falling edge that's triggering the event, you have an inversion bubble on the top. We will see that edge notation in our iStudio as well when we're designing with our functional blocks. So just be aware that that's what we're talking about, clock edges. And the J and K, which act as our set and reset for our output Q, the truth table of what's going to happen with J and K is applied when a clock edge hits. We had two classifications of inputs and related to their relationship to the clock edge. If J and K, if their effect happens in time with the edge of a clock, what kind of input did we call that? Synchronous. It is in sync with the clock edge. It's a synchronous input, meaning we can set up J and K and toggle, change them, change those bits, hit the buttons, flip whatever we want. The effect is only going to pass through the unit at the edge of the clock, when the edge of the clock strikes. And we'll see this in a lot of the homework when we build out timing diagrams. So at the edge of the clock is where the effect happens. That's referred to as a synchronous input. Most or some chips have an ability for us to change the output at any time when we apply a voltage to maybe an internal S and R connection, and those are asynchronous. They can happen at any time. Asynchronous. Yes, question.
When you say edge of the clock, is that the edge of the high signal or the edge of the low?
So it depends on our setup. The question was, which edge are we talking about? And that's determined by the schematic. Our clock, which will be a square wave pretty much. If you have this triangular notch, it'll be the rising edge. So going low to high. If there's an inversion bubble in front of that notch, it'll be the falling edge going from high to low. So that will be important to consider if we are putting a physical waveform from the function generator. So finally, those are some details of the JK flip-flop. And remember that when J and K are 0, it just retains its previous state of Q. And that's called a latch condition. Note that the JK flip-flop has a Q naught that just comes out based on the internal setup. Sometimes we use Q naught. We'll look at some use cases later, but Q naught, or the bar over it, as we know from our algebra, is just the inverse of Q. So we have both available, and this plugs into if our system is active low, active high, or which direction we're counting. So more to come on that. But anyway, J and K can be used to, J can set our Q, K can reset the Q. If you have a 1 on both, we get a toggle functionality. So at each clock edge, Q will toggle from 0 to 1 or 1 to 0. This toggle functionality is critical to building counters that we're moving into today. So the overall umbrella realm we're in, just talking in the space of English language definitions, is sequential logic. When we're talking about logic gates, we were talking about combinational logic. When we talk about sequential logic circuits, and we're going to be talking specifically about counters, the structures or systems we'll make, the circuits will make, count in binary. And then, so from 0, 0, 0, if it's a 3-bit counter, up to 1, 1, 1, incrementing by 1 at a time, and then it rolls back over to 0, 0, 0. Similar to the functionality of a timer you talked about in 179, for example. We have some terminology we need to add. The modulus of a counter is defined by the number of binary states. So we say a counter is a mod 7. That means it has 7 potential output states. Mod 8 would be more common, and it's a power of 2. Because if you have 1 bit, you have 2 potential states, or a mod 2 counter if it's going 0, 1, 0, 1. You have 2 bits, the power of 2, 2 squared, you have 4 potential states. 8 would be a 3-bit counter, you're going from 0 to 7, which is 8 total states, so it's a mod 8 counter on 3 bits. It's just how many different states does that counter possess. So if you're counting from 0 to 255, what would be the modulus of that counter? You're counting 0 to 255.
256.
256, exactly. There are 256 discrete states when you count from 0 to 255, or an 8-bit counter. So that's just the terminology modulus. And you may see some overlap with, the computer science idea of modulus, just a whole number integer operation. But modulus for us means how many states can our counter represent. Here's a block diagram format of a 3-bit counter. And what we need to know when we talk about counters is they're being driven typically by a clock signal, either a continuously repeating clock, from a generator type of signal, or a push button that's incrementing the counter by 1 every time we hit a button, that type of thing. But we have a clock input, and then our output takes the form of binary bits. And typically we number them starting at 0 at the least significant side. So Q0, then we have Q1 and then Q2 counting up. So this is a 3-bit counter that would start at 0, 0, 0. Every time there's a clock edge, it increments up by 1, and it continues to count up in binary until it reaches 1, 1, 1, and then it rolls back to 0. And we can see that in truth table form or in timing diagram form. So we have 8 different binary states that a 3-bit counter can show. So 8 different states, 0 through 7 would be a mod 8 counter. And you can see the counting, just the decimal count here, 0 to 7, or the binary count there, 0, 0, 0 to 1, 1, 1. Timing diagram wise, the bits look like this. One thing to note is in this particular case, it is a falling edge triggered device. And we'll see what that means in just a minute. But we can see this bit, the lowest significance bit, going 0 to high, and then when it goes low again, the next bit goes up. So we're going to look a bit about how to connect JK flip-flops together to produce this counting behavior we see in the truth table. So flip-flops can be used to form binary circuits. Remember, JK flip-flop or JK latch is a type of flip-flop. That's a general kind of terminology for these type of devices. And then we're going to cascade the Qs. So the Q output from one flip-flop will feed in to be the clock of the next flip-flop. And each flip-flop can hold 1 bit. We talked about that last time. You have a 1 or a 0, which is 1 bit. So if we need 3 bits, we need 3 flip-flops. And so that's a mod 8 counter with 3 flip-flops. And at a device level, flip-flop device level, it would look like this. These are 3 JK flip-flops. We have a clock signal coming into our first one. Here are our asynchronous set and reset. Because we have this bubble, what does that imply about that particular input if we have that bubble on the input? It's active low. So the reset and the set are active low. So they're essentially being tied to 1. The reset has a mechanism so you can reset it manually if you want. But basically set and reset will be tied to 1. They're asynchronous set and reset, so you're not interacting or changing the bits outside of the timing of the clock. J and K are tied to 1. And so when J and K are tied to 1, what is the operation of a JK flip-flop? What does it do to Q if J and K are both 1?
It just changes on your toggles.
Toggles, yes, we're in the toggle function if we set J and K to 1. So every clock edge, and based on this signal, which is an inversion bubble and an arrow, and the triangle, is that a rising edge or falling edge? Falling edge, yes. We have the inversion bubble plus the notch. So that's the falling edge of the clock signal. It's going to make Q toggle. You'll note that our Q0 output feeds into the clock of the next one. So the second flip-flop will be clocked by the edge from the first flip-flop, and so forth. The output, as your output count, is just being taken from each Q. So Q0, Q1, Q2. And our timing diagram for this circuit looks like this. We have some clock pulse driving the system. At every falling edge, or one of our bits will increment. So this is Q0, this first one. At the falling edge of the clock, Q0 goes from all, so we are 0, 0, 0, all 3 bits are off. At the clock edge, only Q0 goes high because the clock is directly wired into it. And then when the clock falling edge hits again, Q0 goes low. Well, Q0 going low is a falling edge to trigger this second flip-flop. So at the falling edge of the first, which is 0, 0, 1, that first bit goes back low and the second bit goes high because we got a falling edge. And it becomes 0, 1, 0. So note our count is still going in binary order. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. When that first bit goes high again, then that falling edge goes low. It triggers the second bit falling edge to also go low, which triggers the third bit to then go high. So the sequence continues with the number 4, 1, 0, 0, and 1, 0, 1. And that continues. So the falling edge of each bit is what is structurally driving the next devices. And it's referred to as that clock signal is rippling through. And these are referred to, generally speaking, as ripple counters. Because whatever happens on that clock may propagate through those other devices if it is at the falling edge state. And as you keep going with that count, for 3 bits, you end up in a state where you're at 1, 1, 1. And then the first bit goes low, which makes the second bit go low, which makes the third bit go low. We're back to 0, 0, 0. So physically, this counter will count up from 0, 0, 0 to 1, 1, 1, then roll over and continue counting as long as that cue is going. So this is a mod 8 counter. A lot of our notation will have a reset, just a brief reset activation right at the beginning, and that's going to just start our clock at 0, 0, 0. For our software purposes, it will typically automatically start at 0, 0, 0, or maybe 0, 0, 1. I saw in a few instances. You can visualize the counter as a whole on a state diagram style, which is just starting at 0, 0, 0 and moving through those states. We will use state diagrams a little more later when our state movement is more complex. Right now, there's only one path. It's directly around in a ring. So it's not mandatory that we view it in this way. But in the future, we may have opportunities where if we get to a certain point, maybe we go immediately back to 0. Or maybe we go to a different function entirely. We're going to build towards an idea of a state machine. So a physical digital device that can make have multiple execution routes. But for now, we're just counting in a ring. So this conceptually matches the way you use counters in 179, for example, or timers. One note before we move on deeper, and we'll come back to this terminology more in the future, but we've mentioned that logic gates have a delay. They're not immediate like a wire would be. Putting 5 volts on one end means you have 5 volts at the other pretty much immediately. Logic gates have a brief delay. Flip-flops are the same. When we hit a clock edge, it takes a bit of time for the signal to get from that input JK to the output Q from that clock edge. And the time from when we get the input edge to the output Q change is referred to as the propagation delay. So how long does it take for the signal to propagate through the gate? In many cases, it's 20 or 30 nanoseconds. So quite fast to us as humans, but this is something measurable on our oscopes. We can measure the delay of gates physically in the nanosecond realm pretty easily with our benchtop equipment. And with a ripple counter, where each flip-flop drives the next, those propagation delays compound. So if your first flip-flop has 1 propagation delay, the second one is now 2 delays behind the clock signal. And the third one is now 3 delays behind the clock signal, the third bit. And so ripple counters do reach a point where they cannot have more bits because it's still updating when the clock signal might change again. So if you have a very fast, like gigahertz level speed clock signal, which if you think about your like Intel CPUs, you're at 4 gigahertz clock speeds these days. Ripple counters are not appropriate for high levels of bits because if the total propagation of your highest bit, if it hasn't updated by the time the clock signal hits again, you're in a race condition where you never hit a stable state. So 1 over the total propagation delay gives you the maximum frequency that you can run that system or that ripple counter. Okay, well, there's a slide with some invisible text here. But essentially, what that is showing us is what I just described, which is, and I can't really even see the text here in person, but it's explaining that the number of flip-flops limits the maximum speed. So if you have the propagation delay of 30 nanoseconds, 1 over 30 nanoseconds is the fastest frequency that you can run one flip-flop. And if you have 1 over the number of flip-flops times 30 nanoseconds, that gives you the number of flip-flops that can be part of that ripple counter for a particular speed. So there's a relationship between how fast they can run and the propagation delay. There are a few more specifics in the parameters and how it operates. There's a certain amount of setup time that J and K must be in place before an edge happens, things like that. We'll pick apart the mechanics of this even more in a future lecture. For now, just highlight to yourself, gates have propagation delays. For a 4-bit ripple counter, that would look a lot like this. We're just expanding our functionality we just saw with the 3 ripple counter, so I'm not going to go into the excruciating detail, but we now have 4 bits, one feeding into the next, into the next, into the next. And so we're counting from 0, 0, 0 up to 1, 1, sorry, 0, 0, 0, 0 up to 1, 1, 1, 1 or 15. And then they all reset at once, just by the nature of how they're set up. So this is not like running a loop in software. This is more like setting up dominoes in a row and knocking them down. They only have one way they can fall because of how they physically exist. So there's a 4-bit counter, counts from 0 to 15. What would be the modulus of a 4-bit counter? 16, yes, we have 16 total states, 0 to 15, and then it resets back to 0, 0, 0, 0. We're going to be building things like this in the lab as well. Question, yes?
Whenever it gets to 15, the edge of the clock cycle, does it reset the edge of the bottom one? Does it reset the count or the clock, or what does it reset?
So the question was, when we reach 15, what all gets reset? So there's no change with the clock. It just continues to tick at whatever square wave rate it's set to. And then all the bits, because of how they're connected, will be toggled back to 0 at the same time. So the 4 bits are essentially just sitting here toggling at different frequencies. And at certain points, they line up and all toggle back to 0 at the same time. In mechanics, there are some fun. You can find like a YouTube video of different size, like balls spinning around, and they make different forms and waves as they go based on the different frequencies mechanically. There's a lot of parallel between electrical frequency behavior and mechanical frequency behaviors that some people find interesting. Not a rabbit hole we want to go down right now. But we can use the very same counter circuitry that we just defined to count down as well. So if you've ever been to your favorite fireworks show and you want to count down from 10 to 0 before everything launches, we know counting down has utility as well. We can count down with our circuitry by just using the Q0 bits and using the rest of it identical. So Q is still driving our clocks. So we have the clock in for the first bit, and then Q drives the next clock, Q drives the next clock. We're just taking our output from the Q0. So instead of 0, 0, 0, Q0 will show 1, 1, 1. Then as we increment that clock, the Q0s actually represent a counting down from 7 down to 0 for a 3-bit counter, for example. Or that mod 8. So a mod 8 down counter, mod 8 means it has 8 total states. Down counter means you're taking the output from Q0 instead of Q, represented counting down.
Will there ever be an application for a falling edge and rising edge connecting into one another?
Typically not, because the design tools we would use to make a circuit are based on the assumption of one or the other only. So if you did K-mapping to figure out a sequence of logic, and we'll go into how to do that with this type of system in a little while later. The mixing of rising edges and falling edges is very uncommon. because that behavior is not all mathematically connected, and you disjoint some portions of your system. So no, you don't mix rising and falling edges. Typically, you have all falling or all rising, and then you have all active low logic or all active high. You don't mix and match on one system. Okay, so I mentioned that bit counters will count up to their maximum and then roll over by default. If it's a 3-bit counter, it counts up to 7 and then rolls over. If we don't want to count up to the maximum, we have a way of resetting it on demand when it reaches a value, just using some of our logic gates from before. We have situations where we do this in something like BCD for human binary, where we only count from 0 to 9 and then roll over. We don't want to represent the hexadecimal digits. So there are times when we want a counter to end at a number that is not a power of 2. And so we have the ability to design divide by n counters. So we have a second terminology being added, this divide by, and it is in a replaceable term for modulus. So a mod 8 is also a divide by 8 counter. What that means is the n in the divide by n, so say a 3-bit mod 8 counter is also a divide by 8, is the highest bit frequency is a division of 8 or divided by 8 from the clock frequency. So if we look at the timing diagram, the clock has a certain frequency. Because it takes 2 clock cycles to toggle the first bit, because the first clock cycle makes it go high, second clock cycle makes it go low. The frequency of this 2 to the 0 is what in relation to the clock? It's half of the frequency, or the period is double. Half the frequency. So we have a divide by 2 per bit in relation to the frequency of the clock. So if you have a clock signal, it divides by 2 to the first bit, it divides by 4 to get to the frequency of the second bit, and it divides by times 2 again, 8 to get to the frequency of the third bit. Okay? So if you have a microcontroller system that has a 16 megahertz clock like you had on your Arduino Mega boards, and you want to run a timer at a slower rate, we were able to turn on a prescaler to divide it by 256 or 512 or 1024. All a prescaler is putting that clock through a bank of flip-flops that are going to divide it by a certain amount. So if you want a prescaler of 256, you just run your clock signal through 8 flip-flops, and you've now divided that signal frequency by 256. So the divide by notation is a very functionally useful ability for us to be able to step down frequency of signals. Okay, so the divide by is just about the relationship between your clock signal and your highest bit. More bits means a larger divide by number, and also a larger modulus number. The two are interchangeable. So if we had a divide by n or mod 5 counter, or divide by 5 counter, something like that would look like this. And the addition in this circuit, so divide by 5 means, or modulus 5, which means we need 5 total values, so 0 to 4. So this circuit needs to count from 0 to 4 and then reset itself back to 0. The way we do that is by adding some logic to our reset, asynchronous reset. So we want to count 0 to 4 and then immediately reset when we hit 5 so that it goes back to 0 instead of 2, 5. And we can do that just by putting some logic. 5 would be 1, 0, 1. So we can just do an AND gate between the first bit and the third bit, which is 1, 0, 1 or 5. So it resets when it hits 5. So it'll go 0, 1, 2, 3, 4. Hit 5, instantly reset. Instantly being not accurate, but reset very fast. Just using an AND gate. Note that this is active low, so it becomes a NAND gate to activate that reset. You do have a brief blip on that reset figure because you have to hit 5, there's a bit of propagation delay before your reset goes through. And so you have a brief glitch at 5 before it goes back to 0. But by adding logic to the reset, the asynchronous reset, which we will have in iStudio as well, we can count up to numbers that are not a power of 2. In a state diagram representation that looks like this, where we reset to 0, count up to 4. At this 5 is our glitch state where we reset immediately back to 0 again. So we have a visual representation of that shown as well. 6 and 7 are shown in case there is a power up state, which those happen. If you started at 6 or 7, your circuit would continue to count, but then it would hit reset actually at 111 if we were looking at those outer 2 bits, and jump to reset and then be locked in its pattern. So once we go into design of state machines later on, we do have to consider if we're outside of the flow of where we want to be, does it get back on track? Or does it just count off into infinity somewhere else? Something to consider, but in this case, we're just looking to count mod 5 for this example. Here's a mod 6 up counter with a manual push button. So we're just showing some other examples. Up counter means we take the bits off of Q. It's a mod 6, which means we count 0 to 5. And on the number 6, 110, we need to create a reset. This particular system can reset either by receiving the number 6 and doing an AND between the first 2 ones, or having a manual reset push button. So either of those would trigger the asynchronous reset. So it's a mod 6 up counter with a manual push button. Part of when you read on a particular system, you want to make that system. Part of it is just picking apart the title of it into what are the different hardware pieces required to do that. So mod 6 tells us something about the count range. Counter up counter tells us where we get the outputs. Manual push button reset tells us about this additional logic for the reset. So we do have to pick apart the English language title of what we're being asked to create for these. In physical chip circuitry, it's a historical element that a lot of physical banks of flip-flops that you buy, at least at small scales, will have a bank of 1 and then a bank of 3 flip-flops. And what you can do is manually tie the Q of the output 1 into the clock of the next bank of 3. That's just a historical facet, not a theoretical thing. But where that's going to come out is in some of our labs and data sheets we look at. They may reference, well, how do you make a 4-bit flip-flop out of this one that has a 1 and a 3? Well, you just have your original clock going into 1, then the output of that, just tie it back in, which would be physically wiring it back into the other 3 to get a bank of 4. For that style of chip. Obviously, in our FPGAs, they're all going to be kind of manually created and binned together. So depending on the type of implementation you run into, FPGA versus traditional chips, you may or may not run into that. But I wanted to mention it because a lot of data sheets, that facet still feeds forward, and you'll see it in the textbook as well. And you just physically connect the output of 1 to the clock of the next. So you do need a conceptual understanding of how are these 3 bits connected, and then you can make sense of the hardware, whatever it happens to be. So all of that previous discussion was on the idea of ripple counters, the prior JK flip-flop triggering the next JK flip-flop. What we want to talk about next is a synchronous counter. So we mentioned previously, ripple counters are limited in how fast they can go because the signal, the Q state, has to ripple through the whole thing before the clock signal changes it again. So there's a time, a maximum speed it can go based on that clock speed. For synchronous counters, all clock inputs will come from the same clock signal. And that means they're all being launched, all the flip-flops are being activated by the same starting signal rather than having to have it ripple through each one. And so the maximum speed you can count goes faster. So specifically speaking, what the timers are on a modern microcontroller system are probably synchronous, because we're talking about 8 and 16-bit or more size counters. To make synchronous counters, we do require some external logic, because the bits have different relationships to how they flip. The first flip-flop is tied directly to the clock, as we saw before, but the second is going to have some additional logic connected. Well, let's see. Clock input here, going to the first and to the second as well. But what's different is the second one now has a K connection being made to the output as well. So it's only going to change under certain conditions. And the third bit now has this AND of the first two. So we're going to need to count up to 1, 1 before this bit will get its toggle operation to happen on a clock. So while we don't ripple through every single circuit, there is still potential propagation delay from singular gates, for example. But basically all this is doing is setting up the timing diagram so that, you know, this third bit will only flip when those first two are high. So we're just setting up the logical situation so that the timing counts accurately. But fundamentally, for a synchronous counter, every device is clocked by the same clock input line here. So you are able to go faster, not limited by the bit number, but limited by really the propagation delay of your logic. So you have a much higher speed possibility. There are a lot of packaged versions of these type of chips. If you're making your own digital logic-based wristwatch, hardware only, you might use something like a counter in that with some kind of onboard clock. So that's where we're going to pause with the idea of counters. We basically defined ripple counters and synchronous counters. Ripple counters have one clock input on the first bit and the number ripples through. Synchronous counters take the same clock to each device. And so they have a higher speed ability. In the lab this week, we're going to implement a lot of different forms of counters and possibly in a couple future labs as well. So we'll talk about counters much more as we go. They're a very useful piece of tool and technology for us. Our last few slides that we're going to discuss today are on a couple applications related to 7-segment displays. Or 7-segment LED. You may or may not have ever encountered these. They're a little less, slightly less common than they maybe were 10, 20 years ago, but they're still everywhere. I guess to our Kokomo folks, I'm pointing at a microwave out in our student union here, but the panel on the microwave with a clock on it is going to be a 7-segment style panel, for example, or older car radios, rather than being all LED screen or LCD or whatever kind of fancier graphical technology, used to just have LED-based output that has a very limited range in what it can produce. And the output physical structure was like this, and only certain LEDs would turn on to represent certain numbers. You were interacted with this structure a little bit on the previous test. One thing to note, though, is the arrangement that needs to be turned on for the number 1, the number 2, the number 3. It's not a sequential count of the LEDs. So we do have a decoder chip or decoder set of logic, essentially a lookup table, similar idea to an ASCII table, that says for this binary number, here's which LEDs need to be turned on to make the number 1, the number 2, the number 8, the number 0, so on and so forth. And each of those outputs couldn't be determined manually. This is what you did on your test. It was for the number 1, which one of these segments were turned on, and then you K-mapped it for this input. Here's the K-map results for just one of those segments, for example. I think you just did segment A, actually. You know, I was in school within the last couple decades when I was in college, and some of my digital logic activity was to K-map each segment and build this all on a breadboard, build this decoder chip. That chip is definitely less than $1 on any manufacturer, probably laying around either of our campuses all over the place. Also reproduced digitally very easily. And so the technology moved forward to the point where we don't need to reconstruct a 7-segment display driver at every stage. We can just assume it works and kind of move forward to other things. But in general, these are all just LEDs, and they require resistance, of course. So we have current limiting resistors involved, and we're running LEDs to generate our 7 segments. We'll play with those a little more later on. Our lab does reference 7-segment displays as an output. For us right now, we don't have 7-segment display modules. There is a 7-segment display. It's a PMOD plugin. Kind of, you may be familiar with the Arduino Shield ecosystem where you can put on all kinds of different shields on your Arduinos. There's actually a PMOD ecosystem as well, where you can put a 7-segment display or a real-time clock or things into that PMOD junction on our ice stick. I haven't gone deep into what all we can get there, and I haven't ordered 7-segment displays to plug in there. So when we get to that kind of activity in the lab, we'll just output our output in binary on the lights. And that'll have to do for now. Maybe we'll get some of the fancier peripherals as we go. Okay. One last topic item is the idea of multiplexing and demultiplexing, and this will tie back to 7-segment displays in a moment. But multiplexers are devices that funnel one of several inputs to a single output. And so in this particular case, this multiplexer has 4 different data inputs. There's a selection control, which means which data input will be channeled to that output. So think of if you're sitting and watching TV, these are all the channels, and you're using the remote to flip through the channels. Only one of them shows on the screen at a time. But a multiplexer lets you choose one of multiple input data channels. So, for example, if your system is trying to monitor the smoke alarm in every classroom, maybe you check one at a time. You could put a counter on the select that's counting up. And so you're checking one, the next, the next, the next in a sequence. So rather than doing a lot of things in parallel, a lot of the systems we make will be looking at kind of multiplexing through things and looking in a sequence. We'll talk a little bit later on. And maybe in either 179 or 279, you've potentially talked about like scanning keypads and looking at each button individually through multiplexing. What we're talking about now is the physical electronics that allow you to scan through things and check multiple items. So a truth table representation of our multiplexer looks like this, where we have a selection bit input. So which channel are you selecting? And that chooses which data gets sent to the output. Internally, we don't need to build our own multiplexer, but it is made up of all our basic logic gates. And just by basically using AND as an enable functionality, you can let only one data channel go through to your output. And there are a lot of different hardware pieces of this. If you don't want to buy an entire microcontroller, you just need a multiplexing functionality, which is far more common than a lot of other things. That you just need a multiplexer. There are a lot of, industry standardized packages. You can just buy a multiplexer with so many input pins and output pins. And you would see a data sheet that looks something like this, where you have a bunch of different inputs. You have your selection bits, then you have a couple outputs. With why and why not so active high, active low outputs. Data sheets would include your internal logic. But it's essentially using AND enabling to make that multiplexing work. Okay, so the reverse option is also possible. If you are demultiplexing, that means you have a single data channel and you're selecting one of many outputs to take. the selector bits choose which output the data is going to be sent to. So if you are delivering the mail and you have one of 4 different mailboxes, you can stick it in. The selection bits tell you which mailbox you're going to put the data in, that kind of thing. So multiplexing goes from many to one. Demultiplexing goes from one channel to many. And you select with selection bits where that data is going to go. And you can get as many bits as you need for either of these types of applications. So why introduce multiplexing right now? Well, 7-segment displays use a lot of multiplexing because they can take advantage of how slow our eyes and brains react to changing LEDs. With 7-segment displays, you could wire the 4 data channels and enable to each display, but what is more commonly done to save space is you'll have one data bus going to every light, and then each light will also have just a single enable. So there's some data being sent to all lights at once, but only one light will be turned on at a time. So you'll load up the data for light number 1, for 7-segment number 1, and enable it. Count up by 1. Change the data, enable the second one. Change the data, enable the third. Change the data, enable the fourth. If this is slow enough, we can see that. But if it's fast enough, it looks like these are all on at once. And you've done various experiments with blinking LEDs in your earlier classes, where it might be blinking, then it just kind of looks like it's faded on at a low level, even though it's blinking on and off at a high frequency. You may have encountered pulse width modulation up until now. It's that idea that as long as we change fast enough, we see the averaged effect. And so when you have a bank of 7-segment LEDs, they're being multiplexed to save having to wire data bus from your controller out to the segments for every single segment. You just have one common unified driver bus. And conceptually, why this is really important is because when we build out to like large PC systems and we have big sticks of RAM and processors with a lot of different, bytes of data in a 4 gigabyte RAM stick, for example, we can't have 4 gigabytes times 8 bits number of data channels across your motherboard. It would be as wide as a 4-lane highway going from your RAM to your processor. But with just one data channel and the ability to enable only 1 byte of memory at a time, we can save substantially on the amount of hardware space it takes to get data from point A to point B. We'll put a pin in that for now. Next time, we're talking about counters and clocks.